Welcome to lecture 17. In this week we are talking about basic concepts of optimization part 2. So, in the previous lecture we have started our discussion on optimality criteria for equality constraint optimization problem. We have talked about variable elimination method and we have also talked about method of constant variation. In today's lecture, we will start our discussion on Lagrange multiplier technique. So, we will briefly introduce what is Lagrange multiplier, then we will try to give geometric interpretation of Lagrange multiplier, we will also give economic interpretation of Lagrange multiplier. And in the next lecture, we will take several examples of equality constant problems and solve using Lagrange multiplier. So, the method of Lagrange multipliers gives a set of necessary conditions for candidate optimal solutions of equality constraint optimization problems. So, the Lagrange multipliers basically gives us a set of necessary conditions. In this method, an equality constant problem is converted to an equivalent unconstant problem with help of certain unspecified scalar parameters known as Lagrange multipliers. Each equality constant is associated with a Lagrange multiplier. Their values depend on the form of the cost and constant functions, that means form of the objective function and form of the constant function, functional forms. If the functional form of a constant changes, the value of its Lagrange multiplier also changes. So, let us first take a single equality constant, an optimization problem with a single equality constant. So, we are solving a two variable problem subject to single equality constant. So, the problem statement will be minimization of x 1 x 2 subject to h of x 1 x 2 equal to 0. The method of Lagrange multipliers converts this constant problem to the unconstant optimization problem by applying a parameter known as Lagrange multiplier. So, you get the unconstant function L, which is a function of the decision variables x 1 and x 2 and the Lagrange multiplier, and L is obtained as the objective function plus Lagrange multiplier multiplied by the constant h. I have a single constant, so I have a single Lagrange multiplier. If I have two constants, my unconstant function L will be and so on and so forth. So, this is how you will get the unconstant problem using the Lagrange multiplier. So, basically for each constraint you will define one Lagrange multiplier and you will add the product of Lagrange multiplier and the constraint to the objective function. So, the unconstant function L is known as the Lagrangian function and lambda is the Lagrangian multiplier. Remember, there is no sign restriction on the Lagrange multipliers. We will talk more about it in today's lecture later. If for a given value of Lagrange multiplier, let us say lambda star, the unconstant minimum of the Lagrangian function L occurs at x star and x star also satisfied the equality constraint h equal to 0, then x star minimize the original unconstrained problem. Sorry, the original constraint problem. So, let me repeat. If for a given value of lambda, that means if for a given value of the Lagrange multiplier lambda star, let us say this, the unconstant minimum of L occurs at x star and x star also satisfies the equality constraint, then x star not only minimizes the unconstrained Lagrangian function, but also minimizes the original constraint problem. In other words, the minimization of this Lagrangian function and the minimization of this function f x becomes synonymous. Why? Because at minimum point, that means at x1 x star, the equality constant will be satisfied. So, it will be 0. So, this part will be 0. So, minimum of L will be equal to minimum of f x. So, basically what we do is, given the constants, given the equality constants, we define the Lagrange multipliers. If you have a single equality constant, we will have single Lagrange multiplier. If we have m number of equality constants, we will have m number of Lagrange multipliers. Then we will define the Lagrangian function. The Lagrangian function will be f x plus Lagrange multiplier multiplied by the constant function. Now, we say that the minimization of this Lagrangian function is same as minimization of the original constraint problem. So, now let us look at the Lagrangian function, which is L equal to f plus lambda into h. So, let us consider L as an unconstant function of x 1, x 2 and lambda, that is Lagrange multiplier. Then the necessary condition for this unconstant function can be written as del L del x 1 equal to 0, del L del x 2 equal to 0 and del L del lambda equal to 0. So, del L del x 1 equal to del f del x 1 plus lambda into del h del x 1. Similarly, del L del x 2 is del f del x 2 plus lambda into del h del x 2, which will be equal to 0. And finally, del L del lambda is nothing but same as the equality constant h. So, we need to solve these equations simultaneously, and if we solve these equations simultaneously, we get the candidate minimum points or candidate optimal points as x1 star, x2 star and lambda star. So, the necessary conditions obtained from the Lagrange multiplier method is del L del x1 equal to 0, del L del x2 equal to 0, del L del L del lambda equal to 0. This is for a function with two variable and one equality constant. This of course can be easily extended to n variable function with m number of equality constants. So, x1 star, x2 star, lambda star is the solution of these equations. So, for the given problem, a function with two variable, single equality constant, you have three parameters or three variables x1, x2 and lambda. If you have three equations, you solve them simultaneously, you get x1 star, x2 star, lambda star, let that be the solution. So, this solution is a candidate optimal point. Now, you need to judge whether this is minimum or maximum. So, you can make use of Hessian matrix of L, we can make use of Hessian matrix of the Lagrangian function. So, if the Hessian matrix of the Lagrangian function at the candidate solution point is positive definite, the solution is the local minimum. We know this already. If the Hessian matrix of the Lagrangian function at the solution point is negative definite, the solution is local maximum. So, the first thing to do is to form the Lagrangian function. So, the Lagrangian function can be easily formed from the objective function and the Lagrange multiplier and the constant. Then apply the first order necessary conditions as take the partial derivative of the Lagrangian function with respect to each variable, set them equal to 0. Also take the partial derivative of the Lagrangian function with respect to Lagrange multiplier, set that equal to 0. So, solution of these equations will give you the candidate optimal points. Candidate optimal points will be obtained from the solutions of these equations. Then whether the solution is really minimum or maximum can be inferred from the Hessian matrix of the Lagrangian function. If the Hessian matrix is positive definite, the solution is local minimum. If the Hessian matrix at the candidate solution point is negative definite, the solution is local maximum. So, that was when you have the objective function with two variables and single equality constant. What happens when you have a general problem? So, you have x as n vector and m number of constants you have. So, you simply extend whatever we have learned for the two variable one constant problem. So, now the Lagrangian function will have n plus m unknowns, n variables and m Lagrange multiplier. Why? Because you have m number of equality constants. Each equality constant will be associated with one Lagrange multiplier. So, m number of Lagrange multiplier and n number of variables. So, Lagrangian will be a function of n plus m unknowns, and the Lagrangian can be formulated as the function f x plus lambda 1 h 1 plus lambda 2 h 2 plus lambda 3 h 3 up to lambda m h m, which can be compactly written as f x plus sigma j equal to 1 to m lambda j h j. you can also write down the necessary conditions compactly as del L del xi equal to del F del xi plus sigma j equal to 1 to m lambda j del h j del xi, where your I goes to 1 to n, j goes to 1 to m. So, these are basically the partial derivatives of the Lagrangian function with respect to each of the n variables. So, x I, x 1, x 2 up to x n. Then you have to take the partial derivative of the Lagrangian function with respect to m number of Lagrange multipliers. So, that will give you del L del lambda j equal to h j equal to 0, j equal to 1 to m. So, these are the necessary conditions that you get. So, the solutions to this set of equations, how many equations? N plus m equations. So, your solutions will be x 1 star, x 2 star up to x n star and lambda 1 star, lambda star up to lambda m star. Remember that there may be multiple solutions, and also it may be possible that sometimes you have to take help of numerical methods to find out the solution. Particularly when these equations are nonlinear, you may not be able to solve them analytically, and to find out these candidate optimal solutions, you have to take help of numerical methods. We can also express this general problem in terms of vector notations in a more compact manner. So, minimization of f x, x belongs to n dimensional real space. So, x is n vector subject to h x equal to 0. So, h is a m vector, that means there are m constants. So, first we define the Lagrangian function, which is f x plus lambda transpose h x, L equal to f x plus lambda transpose h x, and the stationary points are obtained from the gradient of lambda with respect to x and the gradient of L, that is Lagrangian with respect to x, and the gradient of or the derivative of Lagrangian with respect to lambda. These are set to 0. So, this is the same, that is, you are taking the partial derivative of the Lagrangian function with respect to each variable, decision variable, and then you are taking the partial derivative of the Lagrangian function with respect to each Lagrange multipliers and setting them to 0. So, now let us talk about the geometric meaning or geometric interpretation of Lagrange multipliers. We will explain this with help of an example. The example we take is an objective function with two variables, and there is a single equality constant. Also, the equality constant is linear. So, the objective function is x 1 minus 1.5 whole square plus x 2 minus 1.5 whole square. So, you can immediately figure out that the minimum of the unconstrained problem is x 1 equal to 1.5 and x 2 equal to 1.5, because at this point the function value is 0. At any other values of x 1 and x 2, the function value will be more than 0. but we have a constant present x 1 plus x 2 minus 2. Here it is possible for us to solve this problem graphically. How? We can draw the contours of the objective function x 1 minus 1.5 whole square plus x 2 minus 1.5 whole square, and then we can plot x 1 plus x 2 minus 2 equal to 0, and from the intersection of the contour and this constant line we can find out the minimum. So, let us now look at the figure closely. This is the contour for objective function value 0.5. The outer one is the contour for objective function value 0.75. So, the objective function increases as you go outerwards, as you go away from the center. That means, objective function value increases in this direction. In this direction, it is increasing. Now, we are minimizing this. At this stage, let us draw the constraint x 1 plus x 2 minus 2 equal to 0, and let us say this and this represents x 1 plus x 2 minus 2 equal to 0. This is an equality constraint. So, this represents feasible region. The solution must lie on the line A B. Since we are minimizing the function, the contour which represents f equal to 0.5 touches the constant line at point C, and this has to be the minimum point. Because this is the point which is feasible as well as has the function value minimum. Note, if you go away from point C in this direction or this direction, you go to the contours with higher function value. Since we are minimizing, point C is the minimum point in the presence of this constraint. Now, what is the necessary conditions for optimality using Lagrange multiplier? This. This we have learnt in the previous slide. So, gradient of f evaluated x star plus lambda into gradient of h evaluated x star will be equal to 0. So, from here you can also write that gradient of f at minimum point or optimal point is minus lambda gradient of the constraint. So, what it means that the gradient vector and the constant vector are on the same line and they are proportional to each other, and this lambda, which is Lagrange multiplier, is the proportionality constant. So, check this. So, calculate del f del x 1, del f del x 2 and del h del x 1 and del h del x 2. So, for the given problem, you get del h del x 1, del h del x 2 as 1 1, and at point C, which is the optimal point, the gradient of f can be evaluated from 2 into x 1 minus 1.5, 2 into x 2 minus 1.5 as minus 1 minus 1. Point C is 1 1. So, put x 1 equal to 1, x 2 equal to 1. So, we get minus 0.5 into 2, which is minus 1. Similarly, you get minus 1 here, and gradient of h is 1 1. So, now look at this, the lambda will be equal to 1. So, the gradient vector is minus 1 and the constant vector is 1 1. So, gradient vector and constant vector lying on the same line. We know the gradient vector directs to the point of increasing function. So, this is the direction of the gradient vector. So, the constant vector is directing in the opposite direction and they are on the same line. This is the geometric interpretation or geometric meaning of the Lagrange multiplier, that at the optimal point the gradient vector and the constant vector will be lying on the same line. They are proportional to each other and the Lagrange multiplier is the proportionality constant. If you now consider any other non-optimal point as D, note that the constant vector delta H is perpendicular to the constant line AB. It was perpendicular at point C also, and the gradient vector for of the objective function is also constant or is also tangent to this contour line. But now you see that delta f and delta h, they are not lying on the same line. This will happen only when the point is optimal. So, at points which are not optimal, the gradient vector and the constant vector, they are not lying on the same line. But remember, the gradient vector will be pointing to the direction of increasing objective function. It will be tangent to the point on the contour. Similarly, the constant vector will also be tangent to the point on the constant line or constant curve. So, at the optimal point, the gradient of the objective function and the gradient of the constant function are along the same line and proportional to each other. The Lagrange multiplier is the proportionality constant. We just compared point C and point D. Point C is optimal, but not point D. So, the geometric meaning of the Lagrange multiplier can be obtained from this expression. Now, what happens to the sign of the Lagrange multiplier for equality constants? Equality constants can be multiplied by -1 without affecting the minimum point. So, let us consider the same optimization problem x1 minus 1.5 whole square plus x2 minus 1.5 whole square, same equality constants, but now instead of x1 plus x2 minus 2 equal to 0, I am multiplying it by -1 and we get minus x1 minus x2 plus 2 equal to 0. That means, the constraint has now been multiplied, the previous equality constant has now been multiplied by -1, everything else remains same. So, del f del x1 del f del x2 remains unchanged, but del h del x1 del h del x2 now becomes -1 previously it was 1. The optimal point is same as point C. So, the gradient vector del f at point C and the constant vector del h, they are lying on the same line. So, del f x star is -1, del h x star is, that means evaluated at point C is -1. So, what we get for lambda is -1. Optimal solution is same as C. So, x1 star equal to 1, x2 star equal to 1, but since you now get the gradient of h at C is -1. So, the lambda star will become -1. So, that this becomes true. So, what we conclude is that the Lagrange multiplier is free in sign. The sign of the Lagrange multiplier depends on the functional form of the constraint function. So, finally, we will give a brief introduction to economic interpretation of Lagrange multipliers. The Lagrange multiplier represents the effect of a small change in the constraint on the optimal value of the objective function. The Lagrange multiplier represents the effect of a small change in the constraint on the optimal value of the objective function. So, consider we have the minimization problem, optimization problem as stated. So, you have in general say n variable objective function and m number of equality constants. So, all equality constants are equal to 0 type. Now, I change the objective function, I do not change the objective function, I change the constant slightly, as instead of right hand side equal to 0, I make the right hand side equal to b. So, h j equal to 0 to h j equal to b j. So, the right hand side of each equality constant is now increased from 0 to b, b j. So, b 1, b 2, b 3 up to b m. So, note the change in the right hand side of the constants. It can be shown that del f star del b j equal to lambda j star. Star indicates the optimal point. So, the rate of change of the optimal value of the objective function with respect to change in b j is equal to the optimal value of the Lagrange multiplier. So, rate of change of the optimal value of the objective function with respect to Bj is equal to lambda j star, which is optimal value of the Lagrange multiplier. So, rate of change of optimal value of f with respect to b is given by the optimal value of the Lagrange multiplier. The change in the optimal value of the optimal function of the change in the optimal value of the objective function per unit increase in the right hand side constant of a constraint is given by the Lagrange multiplier. This is known as shadow price. So, what is shadow price? The shadow price is the change in the optimal value of the objective function. This is objective function per unit increase in the right hand side constraint of a constraint, and this is given by the Lagrange multiplier. So, with this we stop here, and in the next lecture we will take some examples of Lagrange multiplier technique.